In this demonstration, we're going to show how you can optimize the shifting schedule of a transmission to maximize fuel economy. We have a model of a dual clutch transmission. We want to use this to optimize fuel economy, and we'll do that by tuning the shifting schedule. The shifting schedule is a set of thresholds that's used to determine when a transmission should change gears. To find the schedule that optimizes fuel economy, we're going to use the Global Optimization Toolbox and Parallel Computing Toolbox. We're going to use the optimization toolbox to figure out which parameter sets should be tested, or which gear shifting schedules. We'll then distribute those different simulations to different cores on my multi-core machine in order to find the optimal shifting schedule. I'll now switch over to the model so that you can see how this is done. This is the model that we're working with. You can see we have a dual clutch transmission modeled in SimDriveline. You can see the gears, dog clutches, and other components that make up the transmission. We also have a model of the vehicle dynamics as well as the control system. This model, when simulated, calculates the fuel economy, or the amount of fuel used during a drive cycle. And that estimation is based on measured data that we have in a lookup table. The parameters that we are tuning are the shift schedule that's represented in this MATLAB plot. There are 20 parameters that represent the different thresholds for when the transmission should shift up a gear or shift down a gear. The first optimization that we're going to run is a relatively simple one. We've parameterized the shift schedule so that the entire schedule can be shifted based on a single parameter. We're going to use the optimization algorithm fmin_search to try and find the value of this parameter that results in the best fuel economy, or the least amount of fuel used. This is the parameter that will vary, and this is our objective function, which simply pulls the value of the fuel used during the simulation from the results. We're going to limit the number of iterations to 6 in order to let this optimization run in a reasonable amount of time. So I'm going to run this script, which will start the optimization. You'll see that there are two plots on the screen. The one on the left shows the progress of the optimization. The blue line represents a parameter sweep that we ran before, and the red dots that are being added to the line are steps in the optimization. The value of the parameter is shown along the x-axis. As that parameter value varies, we update the shifting schedule in this plot. So you can see that the slopes of these lines are changing as the optimization varies the shift schedule parameter. Down in the command window, we see the progress of the optimization. And this column here, the min f of x, that shows the amount of fuel being used during this drive cycle. We can see that after this number of simulations, that the optimization algorithm has found much better values for this single parameter, and that the shift schedule is improving. Because it's an unconstrained optimization, sometimes shifting schedules will be tested that don't make any sense. But we can see that that led to a higher amount of fuel being used, and the optimization is coming back towards the minimum point. At this point, the optimization is complete, or it's stopped because it reached the maximum number of iterations, and we can see that the value of the amount of fuel used is much better than what we started with. Now we'll progress to a more complex optimization, where we permit the optimization algorithm to change all 20 parameters. In order to do this, what we're going to use is a different algorithm. So instead of using fmin_search, we're going to use an algorithm that will find the global minimum, and that is pattern search. We're also going to use parallel computing, and by doing that, we will simply set the parameter for use parallel to always. This optimization with 20 parameters would take far longer to run, so I'm simply going to show you what the optimization would look like in a recording. So this animation shows what the optimization would look like, and you can see that all of the 20 parameters are being varied. It has a lot more freedom than the optimization we ran before, so we can see that many of the parameters are varying dramatically, and the lines are shifting around quite a bit as well. This optimization, or recording what you're seeing here, was actually run on a single core so that I could record this animation. However, we have the power to run this in parallel, and that would speed up this optimization considerably. By running this on one core, varying 20 parameters with a simulation that takes about 4 or 5 seconds to run, this took about 13 hours. If we were to distribute these simulations among multiple cores or among multiple machines, we could reduce that time significantly. So if I just had a quad-core machine, this optimization would take about 3 hours, and you can imagine that it could go faster from there. You can see the messages down at the bottom, similar to what we saw before. To this point, nearly 3,000 simulations have been run, and we can see that the amount of fuel being used has dropped. We started at I think 3.341 or so, and at this point we've improved the fuel economy by about 5%. So the optimization will run to completion, and it will come up with the optimum shifting schedule, which is the one I showed you in the beginning on the slide. So with this demonstration, we've seen how we can use parallel computing and optimization algorithms to find a gear shifting schedule that optimizes fuel economy.